Alrighty, so this week is oil week. We're pretty much only talking about oil this week. Today we'll talk about how oil is created and we'll learn about salt domes. On Wednesday we'll learn about oil spills, and then on Friday we're going to learn about hydrocarbon seepage in the Gulf of Mexico, like natural seepage. So the goal for today are to understand what hydrocarbons are, to learn about the formation of oil and natural gas, to learn about extraction and refinement of petroleum and hydrocarbons, and to understand what a salt dome is. Oh yeah? Unwillingly. Why is that? From your degree? OChem? Yeah, I bet. Well, today will probably be a lot of review for you, but I think we're going to cover a little bit more than an OChem course would, and I think you'll learn something. So the goal for today are to understand that mud that contains at least 1 to 2% organic matter might be transformed into source rock, which eventually produces oil and gas deposits. It takes 60 million years for dead animals to become liquid hydrocarbons, and therefore oil is classified as a non-renewable energy source. And you'll learn that a single salt dome can have many associated oil reservoirs at a variety of depths and locations around the dome. So what is oil? I'm going to use a number of these terms throughout the lecture, so I just figured we would start off by defining them. So hydrocarbons are any compound of hydrogen and carbon, such as any of those which are the chief components of petroleum and natural gas. Petroleum is a liquid mixture of hydrocarbons, and it can be present in certain rock strata and can be extracted and refined to produce fuels. And oil it can be used in the same way as petroleum is, so it's just a liquid derived from petroleum, especially as we use it for fuel. So petroleum and oil can really be used interchangeably, at least in the purposes of this course. Natural gas is a flammable gas consisting largely of methane and other hydrocarbons, and it occurs underground in association with petroleum, and it too can be used as fuel. So oil and natural gas are often found together. And then coal, which we won't be talking too much about in this course, but I figured I would include it on this list anyways. This isn't a term that you have to know for this course, but it's a combustible black or dark brown rock consisting mainly of carbonized plant matter. And this is found in underground deposits and widely used as fuel as well. Coal is more of a land-based product, so we don't cover it extensively in this course because, of course, this is a coastal oceanography course, and coastal oceanography is generally, in terms of fuel extraction, concerned with oil and natural gas. So that's the main focus here. All right, so this all starts with organic matter, with living things. This whole process of creating oil and gas, it comes about when a living organism dies. And typically, when an organism dies, it doesn't get incorporated into oil. What generally happens is it gets recycled in a couple of different ways. It can either be eaten by predators, scavengers, or bacteria, or it can be recycled through exposure to ambient air or oxygen-rich water, in which case the materials in that organism oxidize. And when I say they oxidize, I mean they combine with oxygen and break down into some components like water, carbon dioxide, nitrates, sulfates, phosphates. And then all of those things can nourish new plants, new phytoplankton. If a living organism is not recycled after it's dead, a tiny proportion of the organic matter might be incorporated into a deposit that will eventually become oil or gas. So what happens is it'll sink to the bottom and it gets buried by small amounts of fine sediments where it is preserved. It's important to know that this preservation only happens under anoxic or no oxygen conditions. So those conditions are necessary to preserve the organic matter because they restrict the degradation of that organic matter by microbes. So that prevents microbes like bacteria from eating that organic matter and incorporating it into their mass. And it prevents that material from oxidizing. So you have to have it sinking to the bottom, buried by small amounts of sediment, under no oxygen conditions. All of those things must be true for the possibility of forming petroleum and natural gas from that matter. So the mud that accumulates this way, over time it accumulates and it hardens to form source rock. And source rock is formed from mud that contains at least 1 to 2% organic matter. And the source rock is the rock from which the hydrocarbons can be derived. So this rock will eventually produce oil and gas deposits. There are a number of specific requirements that are necessary to produce this source rock, or produce mud with this amount of organic matter. First of all, you need a hot climate generally that's conducive to the growth of large quantities of plankton. That way you get a lot of living organisms that die and then are incorporated into that mud. You could have a location near the mouth of a major river, which carries a lot of plant debris. So that would really help the accumulation of all this organic matter at the bottom. And you need to have no nearby mountains that could limit the volume of organic sediment within the rock. Or that could limit the volume of inorganic sediment within the rock. So you can't have too much rock material, too much mineral sediment accumulating within this mud. It needs to be mostly organic. So that means that you can't have nearby mountains that are eroding away and pushing a lot of sand and inorganic sediment into this mud layer. It needs to be, a large proportion of it needs to be organic matter. So you can see there are a lot of requirements to produce petroleum. So it's not that common of a thing that gets produced. It's really just under special conditions that source rock is able to form. And those special conditions largely existed during the Jurassic. So the late Jurassic was a time of significant source rock accumulation. This was a time when marine waters were flooding the rifts that were forming the Atlantic Ocean. And so here we had marine waters flooding all up and down these rifts. Other areas, like in Southeast Asia, were also experiencing rifting, and these formed shallow seas or lakes that were just temporary. Also at this time, sea level was at a maximum, which turned the edges of some of these land masses into shallow seas, as well as a large portion of the interior of Gondwana. And you can see here all of these locations that are colored like orange or pink or green or purple. These are locations where source rock was formed. And so you can see by shallow seas inundating the edges of these land masses, that would be a location of source rock. Shallow seas inundating this portion of Gondwana, that would be a location where source rock was formed. And then over here with the rifting in Southeast Asia, again, we get the source rock forming. Also at the time, the climate was quite warm, and this supported a lot of life, including a lot of phytoplankton. And so you got a lot of organisms that lived and then died and sunk to the bottom. And as a result of all of these things happening in the Jurassic, most of our hydrocarbon reserves that we use today began formation during this time, during the Jurassic. I don't know why that says the formation of a hurricane. It's definitely not the formation of a hurricane. This is the location of different oil reserves that were formed during the Jurassic. Okay, so once you have source rock form, then it has sediment that accumulates on top of it. And so this would be the source rock. You get sediment layers accumulating on top of it, and the weight of the accumulating sediments very slowly pushes the source rock further under the Earth's crust. This is a really slow process. It really only goes by a few meters to a few hundred meters every million years or so. So really slow. And this gradual sinking is called subsidence. So the source rock subsides into the Earth's surface, and as it sinks below ground and the heavy sediments accumulate on top, the source rock gets subjected to increasingly high temperature and pressure. Under these high temperatures and pressures, the nitrogen, sulfur, and phosphorus atoms are gradually converted into oil or gas. And because oil and gas are lighter than the surrounding rocks and sediment, they'll actually rise up through the source rock and through some of the porous rock that surrounds the source rock until eventually they reach an area that's impermeable, like this clay layer here. And that would be a structural trap, which is a location in the rock where oil and gas pool and they form a petroleum reservoir. So you see oil and gas forming a reservoir underneath this structural trap of clay. As that source rock sinks, it will form oil and then gas depending on how deep it is underneath the Earth's surface. So at a depth of between 2,000 to 3,800 meters, source rock turns into oil. And then as it sinks further, between 3,800 and 5,000 meters, then the liquids become increasingly lighter, and then gradually you get those liquids turning into natural gas. Once the source rock sinks below a deep of around 8,000 meters, it's no longer producing hydrocarbons because the temperature at that point is too high. So you get kind of the sweet spot between 2,000 meters and 5,000 meters where that source rock has to sink in order to produce oil and gas. You also get a, depending on the qualities of the source rock, it may be more likely to generate liquids or gas. So the proportion of liquids and gas generated depends on the type of source rock. If you get source rock that's composed of organic material from animal origins, then it's more likely to produce oil than gas. And if you get source rock that's composed of organic material from plant debris, then the source rock will produce mostly gas. It takes 60 million years for the dead animals that form the source rock to become liquid hydrocarbons. And so this isn't something that once we use it up, it can easily be reformed. And that is why oil is classified as a non-renewable energy source. So let's talk about how oil is extracted from the earth and then made available for us to use it. So oil can be classified according to its weight: light, medium, heavy, or extra heavy. Light and medium oil will flow like a liquid. And so they flow naturally to the Earth's surface. If you're able to drill through that structural cap, then they'll start flowing to the Earth's surface. And they're generally extracted from the ground using vertical drill holes and pumps, like this pump that you might see on land that's used for oil extraction, that's called a jack pump. Some of the light oil might be trapped in non-porous rock formations like shale. And so shale would be like layers of rock, and you might have oil in between those layers. And it might be really difficult or impossible to get that material out using a vertical drill, which would only be able to get down to maybe a layer in the shale and not any further. And so there are a couple different ways you can get oil out of a situation like that. You can use horizontal drilling to kind of get in between those layers of shale. And you can also use hydraulic fracturing, which we know as fracking. And fracking is the process of injecting liquid at a high pressure into the rocks to break apart the rocks and then be able to extract oil or gas. So we use fracking when there is oil in an area where it's really kind of hard to get at it because it's trapped in rock formations. If oil is not light or medium, if it's heavy or extra heavy, we call this type of oil sands. And this is material that is essentially a solid. It's too thick and heavy to be pumped through pipes unless it's processed first. So really, oil sands are simply a deposit of loose sand or broken up stone that contains petroleum or other hydrocarbons. When you have oil sands near the surface, like within 70 meters of the Earth's surface, you can use surface mining. And so this is a picture of a surface mine of oil sands, which sometimes are called tar sands. About 20% of oil sand reserves are close enough to the surface to be mined. And essentially, you just use large shovels, large digging equipment to scoop the oil sand into haul trucks, and then that sand is transported to crushers to crush up any rocks that might be in that sand, and then it's mixed with hot water and pumped by a pipeline, because at that point, since it's in hot water, it's relatively liquid. Then it can be pumped by a pipeline to a plant called an upgrader, and the upgrader is where the oil will be separated from the sand, clay, and water that was used to pump it there. And so there are a number of steps, you see, to be able to get oil out of oil sands, which makes it a more expensive mining endeavor. And that's just at the surface. So if oil sands are existing in deeper layers, deeper than around 70 meters, then they have to be recovered in situ, which means in place. And so there needs to be special technology to be able to process that oil to a point that it can be pumped out of those locations. So the oil is separated from the sand below ground, right in the deposit of the tar sands. And to do this, a large quantity of water and natural gas are used to heat the oil sands with steam until they become fluid enough that the oil can be pumped to the surface. And so that's even more expensive to do and requires a lot of technology to extract those resources. So sometimes in the news, you'll hear that a lot of our easy-to-access oil reserves have already been tapped. And so that would be those oils that are light and medium oil that can flow naturally to the Earth's surface and aren't blocked by anything. But the harder to reach oil is the oil that we're kind of tapping now. And so that would be some of those locations that need something like fracking or even oil sands. So we have to put in more effort to be able to mine these sources. Okay, so once you have crude oil, you can refine it into a variety of different fuels that we use to do a variety of different tasks. And so here you can see a number of these different fuel types and what they're used for. Of course, gasoline is used for cars, kerosene used for jet fuel, diesel used for diesel fuels. You got some lubricants, and even down here, asphalt for roads and roofing comes from this crude oil. And to do this, to separate the oil into all of these usable products, you need to refine it. So petroleum refineries change the crude oil into petroleum products for use as fuels, paving materials, and materials used for making chemicals. All refineries have 4 basic steps. First is the separation, which is piping the crude oil through hot furnaces. And so the resulting liquids and vapors will be discharged into this column. And so that would be separation. And then conversion happens inside the distillation column, where the liquids and vapors will separate into different petroleum components according to their boiling points. And so the lightest materials are going to be up here and extracted as gases. And then the heavier materials are going to sink to the bottom and can be extracted as heavy fuel oil or asphalt. Come here. You can come down here. You can come to class. There you go. She doesn't want to come to class. She just wants to bother me. Okay. And so after conversion inside the distillation column, then the third step is treatment. And so this is where the finishing touches occur. And this is where, for instance, gasoline blends are made. You might have a specific octane level or vapor pressure ratings that need to be reached for a certain product. Any other special considerations that determine the gasoline blend. That will be done in the treatment phase. There she is. And then finally, you have storage. And so both, yeah, my new guest lecturer, she's got a lot to say. So I probably don't want to give her any sort of soapbox. And the final step is storage, where both incoming crude oil and then the outgoing final products are stored temporarily in large tanks on a tank farm near the refinery. And then this material can be transported to its final destination via pipelines, trains, and trucks. All right, any questions about oil formation or refinery before I move on to salt domes? Cool. Okay. So salt domes have a lot to do with oil, actually. So I figured I'd bring them up in this lecture. You will hear about them more in our lecture on Friday, because they have a number of features that form around them that make interesting features in the deep sea and the Gulf of Mexico. So we'll definitely talk about them. So introducing salt domes. A salt dome is a mound or a column of salt that has intruded upwards into the overlying sediment. They form in a sedimentary basin where a thick layer of salt is overlain by younger sediments of significant thickness. And so you have a thick layer of salt that is deposited, for instance, when a sea evaporates. And then over that, you have a large amount of sediment, a nice thick layer. And the salt will be extruded through that sediment and can push to the surface in a bubble. Salt dome bubbles can rise thousands of feet above the layer of salt from which they began growing. And so these can be quite tall features. And the growth of the dome is accomplished by the migration of the salt into the dome from the surrounding areas. And so you can see here the salt is moving from the surrounding areas into the dome itself. And it's migrating into this dome because it's compressed by the weight of the overlying sediments. So it's just kind of like oozing. All right, you. That's enough. Go away. It's just kind of oozing after being pressed down. It's oozing up into the salt dome. Salt domes were an almost unknown geographic feature, or geologic feature, until an exploratory oil well was drilled on Spindletop Hill near Beaumont, Texas. And this was in 1900. At a depth of about 1,000 feet, the well penetrated a pressurized oil reservoir that blew the drilling tools out of the well and showered the surrounding land with crude oil until the well could be brought under control. And these are some people that had gathered to watch this spout of oil spilling out at Spindletop Hill. This was a really productive well. The initial production from the well was over 100,000 barrels of crude oil per day. And this was a greater yield than any previous well had ever produced. And so after this success, the Spindletop discovery ignited a drilling spree on similar structures across the Gulf Coast. And so they were looking essentially for mounds, for salt mounds. And some of these wells struck oil, and so geologists decided to learn more about these salt dome structures and the reasons why they were such a great source for oil. And so here's the reason why you can find oil associated with these salt domes. So as a salt dome grows, the rocks that it pushes upwards, those rocks are arched, and the upwards arch allows oil and natural gas to migrate up to form reservoirs where they're trapped there next to the salt dome. Also, the rising salt can cause faulting. So you can see there are cracks in this rock here. And these cracks in the rock allow oil and gas to flow up till the next structural trap and form little reservoirs there. And so a variety of different locations around a salt dome can form oil and natural gas reservoirs, and you can see them at a variety of depths and locations around a salt dome. So if you were to drill around a salt dome, you could drill around the top and find some reservoirs, and then most notably, you'd be able to drill along the sides of it, and all down the sides, you'd probably find some oil and natural gas reservoirs. So a great location for drilling. Salt domes also have another resource that can be mined. They are sometimes overlain by rock that contains significant amounts of elemental sulfur. And some salt domes have enough sulfur in the cap rock that it can be economically recovered. And cap rock would just be the rock that's right above the salt dome. And to recover sulfur, you would drill a well down into the sulfur and then pump superheated water and air down the well and melt the sulfur. And then that sulfur is kind of like a frothy slurry. It would rise to the surface, and then you would build a well to collect that at the surface. This isn't really a cost-effective way to mine sulfur, at least not yet. So today, most sulfur is produced as a byproduct from crude oil refineries. So it's easier just to take it as essentially a waste product from refining crude oil than to actually mine it. But sulfur mining does occur in some places, and in some of those places there are salt domes that sulfur is coming from. So even though it's not cost competitive in most cases, it still is a source of sulfur. We specifically want to talk about salt domes in this course because there are many salt domes in the Gulf of Mexico. So the Gulf of Mexico has a whole belt of salt domes lying beneath the surface. So this would be the continental shelf of the Gulf of Mexico. This is the Mississippi River Delta. And these salt domes, as you can see, they lie offshore essentially from the panhandle of Florida all the way throughout the coast of Texas. There are over 500 salt domes that formed as the Gulf separated from the Atlantic Ocean. There were periods where the Gulf completely dried out and filled up again and dried out and filled up again. And so salt was deposited on the bottom of the Gulf of Mexico, and sediment from the Mississippi River covered up these salt deposits. And then that's why you have so many salt domes that have been formed on the shelf. So you got a thick layer of salt and a super thick layer of sediment overlaying it. The salt domes in the Gulf are huge. They're thousands of feet tall and several miles in diameter. Here's a close-up picture of what these domes look like. You see these pits that form when the salt domes are the salt gets exposed to water and then dissolves, and then you get those salt domes kind of collapse. And so these are locations where salt domes have collapsed. But there are other locations where the salt dome is fully intact. And many of these salt domes are associated with oil and natural gas reserves, which is one of the reasons why the location offshore on the shelf of the Gulf of Mexico is so productive for oil and gas, because we have all these features that allow these super productive wells to form, or super productive reservoirs. So this is a pretty special feature of our coastline, our offshore area. In your readings, you read a lot about Avery Island when you were reading about birds and birds being hunted for feathers, and then eventually these bird sanctuaries forming, and one of which was Avery Island. And Avery Island is also interesting because it is a salt dome. So salt domes can stretch far inland in states bordering the Gulf of Mexico. That's because at various times the sea level has been pretty far inland. And as that shallow sea evaporated, salt gets deposited on what we now consider land, but was then a shallow sea. So they can stretch far inland, and Avery Island, which looks like it's somewhat inland and is the home of Tabasco sauce and a famous bird sanctuary. This is actually a salt dome that's surrounded by salt marsh. And then it's interesting to know that salt from the island is actually used to create the signature hot sauce. And so you wouldn't have Tabasco sauce without salt domes. It's actually a pretty high mound. At its highest point, it rises 163 feet above sea level. I think my house is like 11 feet above sea level, so that's pretty high. It's pretty high up there. This is a picture of Avery Island as viewed from above. You can see, even though it's not an island surrounded by water, it's surrounded by salt marsh. And so to get there, you need to travel via bridges. And it's somewhat raised in like a hill. Other salt domes that are well inland, at least they're well inland today, have been used for a variety of purposes other than mining salt to make hot sauce. So these salt domes have been used to create the Strategic Petroleum Reserve. And the Strategic Petroleum Reserve is emergency crude oil that the United States stores to help weather disruptions in oil supply. And so we don't want any sort of disruption in oil supply to completely take us off the grid. We've got enough to last some time, even if we don't have a great supply. And I don't know about you, but when I used to think about the Strategic Petroleum Reserve, I would think about hundreds of thousands of barrels of oil, like stored in some warehouse in the desert. But this is not actually the case. And so when the US government decided to create the SPR in the mid-1970s, it acquired previously created salt caverns, which were evacuated salt domes, to store the first 250 million barrels of crude oil. And so they're stored underground in these caverns created from salt domes that have had all the salt mined out of them. This was the most rapid way to begin securing the emergency supply of crude oil, initially following the oil shocks of the 1970s. And so they wanted a place where they could store a lot of oil fast, and these salt domes provided an opportunity for that. And it's far safer than storage of oil in barrels on land. So there are 4 major oil storage facilities that were formed from salt domes in the Gulf Coast region of the US, and these are the 4 here, 2 sites in Texas and 2 in Louisiana. And then as the Strategic Petroleum Reserve expanded, additional caverns were created specifically for storage. But these 4 were the originals, and they were created from salt domes. And then finally, perhaps the best use of salt domes, it turns out, is as a storage area. So now people are talking about using these salt domes to store hydrogen. So there was a lot of excitement earlier this century about hydrogen as a fuel source. The lightest element on the periodic table, they're thinking that it was going to solve a number of our energy needs. Everything from portable devices to high-rises were going to be cured and fueled by hydrogen. But it turns out that hydrogen storage is a huge problem. So when you're going to be creating a large amount of hydrogen for use in energy, it's even harder to store than radioactive materials. Because, it's flammable and takes up a lot of space because it's a gas. And so it turns out that salt domes are now being viewed as a possible storage storage site for hydrogen. Salt domes near Salt Lake City, Utah have been tapped to store hydrogen gas. This is an image of Salt Lake City, Utah, and some of the salt ponds located there. And if these locations can safely store hydrogen gas, it may enable the use of hydrogen as an energy source, because a lot of the technology has been figured out. It's mainly the storage problem that has to be solved. And so potentially with these new advances in using salt domes as storage, we will have hydrogen as an energy source in the near future. Pretty cool. All right, so today you learned about hydrocarbons, the formation of oil and natural gas, and extraction and refinement, and then salt domes and all of their uses. And we are right on time, so I guess I was right to not plan any activities today, because I wouldn't have been able to do them anyways. So I will see you guys on Wednesday, and I will hopefully not have so many problems starting class. I apologize for the late start.